Hi everyone! Today we are going to solve for all the Pythagorean triples that are a, b, c natural numbers such that a squared plus b squared is equal to c squared. But we will do this by using the Gaussian integers. The symbol for this set will be z of I. And that consists of a plus bi, where I is of course the square root of -1, with a and b integers. So here you can see all the Gaussian integers. Now let's look at some similarities between the Gaussian integers and the real integers that will be very important for the proof. And the first is the norm function. The norm of a Gaussian integer is defined as a squared plus b squared. While in the normal integers, the norm of n is just the absolute value of n. So let's give an example of z equals 3 minus 4i. The norm is equal to 3 squared plus 4 squared, which is 25. And then we are going to look at what we call units. So a unit A is defined as follows. There exists a b in the Gaussian integers such that a times b is equal to 1. So it is a multiplicative inverse. Now in the integers you will be much more familiar with units, because a unit A is also defined as there exists a b in z such that a times b is equal to 1. Now this means that the norm of a should divide 1. But that leaves only two options, that a is equal to 1 or a is equal to -1. And these are indeed both units, since -1 times -1 is equal to 1. So the set of units in z is equal to 1 minus 1. Now in the Gaussian integers it is a little bit more complicated, since it follows that the norm of a divides 1, but we now have more options. We have the options a is equal to 1 and a is equal to -1. But we also have the options that a is equal to I, which also has norm 1, or a is equal to -I. And indeed, they are all units, since, for example, I times -I is equal to -I squared, and this is 1. So both these numbers are units. So the set of units in z of I, Gaussian integers, is equal to 1 minus 1 I and -I. 4 units. Now another really important similarity between the integers and the Gaussian integers is that they both have a unique prime factorization up to units. So let's clear the board and look more clearly what this prime factorization looks like. Let's look at the unique prime factorization. In the integers, I think you all know this. If p is a prime, that means that p is not -1, 0, or 1, and if p can be written as q times r, then either q is a unit or r is a unit. So either q or r is equal to 1 or -1. If n is composite, then n is not -1, 0, or 1, and it can be written as q times r, where they are both not units. So every element in Z is either a prime or composite. And the unique prime factorization means that we can write n as a unit times all primes. And to be clear, a prime can be multiplied by a unit that doesn't change anything. So the prime 3 is equivalent to the prime minus 3. They represent the same primes. Let's now look what happens in Z of I. Well, in Z of I, P of Z of I is a prime if P is not in 0, 1, minus 1, but also not the units I and minus I. So these four are the units. Such that if P is equal to Q times R, with Q and R in the Gaussian integers, then Q is a unit or R is a unit. So that's a prime in the Gaussian integers. Now let me give you a theorem. If P is an integer and P is prime in Z, and P is congruent to 3 mod 4, then P is prime in Z of I. So for example, the prime P is 3 is definitely 3 mod 4, and it is prime even in the Gaussian integers. But for example, 5 actually factors in 2 minus I times 2 plus I. So 5 is a prime in the integers, but it is composite in the Gaussian integers, since it factors. This is equal to 4 minus 1, which is 5 indeed. Now let me give you a second theorem that states that if Z is an element of the Gaussian integers and P divides Z with P prime, then it follows that the norm of P also divides the norm of Z. So for example, the norm of this 5 in the Gaussian integers was a squared plus b squared. So this is 5 squared plus 0 squared, which is 25. Now notice that the norm of this Gaussian integer, 2 minus I, is equal to 2 squared plus 1 squared, which is 5. So we see that the norm of 2 minus I divides the norm of the number 5. But since the theory may be a bit complicated, I will give 3 examples where I calculate the unique prime factorization of Gaussian integers. Now we can finally start with the proof. We know that A, B, and C are co-prime and that the equality holds. So since A and B can't be both even, let's take, without loss of generality, that A is odd and B is even. And because A squared will be even and B squared will be odd, that will mean that C will also need to be odd. And now comes the magic of this proof. We are going to factor the left-hand side into A minus BI times A plus BI in the Gaussian integers. And now let's assume that some lambda, which is not a unit, divides both these factors. So lambda is a prime that factors A minus BI and A plus BI. So if this lambda exists, that would mean that A minus BI and A plus BI wouldn't be co-prime. But This would imply that lambda divides the difference of these two, and that will be 2bi, and that lambda would divide the sum of these two, which is 2a. Now, the I is just a unit in the Gaussian integers, so it simplifies to lambda divides 2a and lambda divides 2b. Now, the first case, that lambda would divide 2, this means that lambda divides 1 minus I times 1 plus I. But these two primes have both norm equal to 2. So the norm of lambda would be equal to 2. But that would mean that the norm of C would be even. Since lambda is a factor of this and this, it also has to factor C squared. So that means the norm of C is even. But we know that C is odd, so this norm will be odd, because the norm of C squared would be C to the power of 4. And if C is odd, then C to the power of 4 is also odd. So this case is not possible. Case 1. Now case 2 would be that lambda divides A and lambda divides B. But since A and B are co-prime in the integers, that means that A and B are also co-prime in the Gaussian integers. So this possibility is also not true. Now this means that A minus Bi and A plus Bi are actually co-prime. And now think about this. If you multiply two co-prime integers and it gives a square, that means that they are both a square up to a unit. Let's look at this in Z. 36 is a square. It is 6 squared. Now if this has to consist of two factors that are co-prime, it has to be 4 times 9. Now that are both squares. Now it could also be minus 4 times minus 9. This gives also 36. So they can be multiplied by a unit. In this case, minus 1. So we conclude that, for example, A plus Bi must be equal to a unit times another Gaussian integer squared. So this is a Gaussian integer. But now since minus 1 is equal to I squared, if the unit would be minus 1 or minus I, we can bring the minus sign into the square by multiplying z by I. So this square will be moved into this square. So we are actually left with two options. That is A plus Bi is just equal to z squared, or A plus Bi is equal to I times z squared. So let's now finish the proof with these two cases and clear the board. So these are the two cases. Either a plus bi is equal to z squared, and if we take m and n integers, then this would be n plus mi squared, or a plus bi is equal to I times z squared. Let's start with the second case. This would mean that this is equal to I times n squared plus 2nm minus m squared. So this would mean I forgot an I. So this would be n minus 2nm plus I times n squared plus m squared. But this a was odd and this is even. So this case won't work. Then only the first case remains. So a plus bi is equal to n plus mi squared, which is equal to n squared minus m squared plus 2nm I. Now, you can see that this has to correspond to a, which is the real part of the Gaussian integer, and this part has to correspond to b, which is the imaginary part, which is the imaginary part of the Gaussian integer. So this gives us that a is equal to n squared minus m squared, and b is equal to 2nm, and c is equal to the square root of a squared plus b squared, which will be the square root of n minus m squared plus 2nm squared, and this will be equal to n squared plus m squared. And n and m have to be integers. So now we are almost done. We have that a, b, c that are solutions to this Diophantine equation, which are the Pythagorean triples, is equal to n squared minus m squared, 2nm, and n squared plus m squared. So now let's plug in some integers to see what this gives. Let's plug in n equals 3 and m equals 2. This would get us 9 minus 4, 2 times 3, which is 12, and 9 plus 4. So this gives us 5, 12, 13, which is indeed a Pythagorean triple. So now by using properties of the Gaussian integers, we found all the primitive solutions. Thanks for listening, and don't forget to like and subscribe.